Welcome back to Principles of Electronics. This is lesson number 9. Today we are going to be talking about transistors. Now, I get asked the question every once in a while, how did they come up with a name like transistors? Well, sometime long ago, somebody said, you know what we need? We need current transferring resistors. That's what they said, and out of that came transistor. True story. All right, there are two types of transistors that we're only really going to discuss one, and there's two main types: a bipolar junction transistor, otherwise known as a BJT, and then a field effect. A field effect, MOSFET, JFET. Sometimes if you look at a power circuit, you'll see these big transistors on heat sinks. These absorb a lot of power. They can take a lot of amperage. We're not going to talk about those today. We're going to concentrate on the bipolar junction transistor. Now you can see the picture. It's a 3-pin piece. Inside this little piece of silicon, just like we talked about with diodes, there is some PNP or some N-type and some P-type material. There's two different types of bipolar junction transistors that we're going to discuss, but let's start with the pins. There's, like I said, 3 pins, and usually in this configuration you can kind of see that there's a flat spot on this. What I like to do is say, well, that from a top view kind of looks like this, and if you look at the pins coming out, normally, not every time, you have to check the specification, but this is the emitter, this is the base, and this is the collector. As they relate to the pins, this is the emitter, this is the base, and this is the collector. So E is emitter, B is the base, and C is the collector. That's the terminology that we'll be using. Now, there's a couple different symbols, and I'm going to try to do them both at the same time. There are two types of bipolar junction transistors. There's what's called the NPN, and then there's the PNP. Oop, that's a D. PNP. And as you can imagine, you have 3 pins, and you have 3 different types of material here. So, as you would think, there is a N-type, and then a P-type, and then an N-type. 1, 2, 3, and there's your 3 pins for your NPN. And the same thing over here, except this is a P, this is an N, and this is a P. Same 3 pins. So this is a NPN, and that's the silicon structure of what's inside of this package, and a PNP type, which is what's inside that package. All right. The symbols for each one of these, they are a little bit different, and it's important to distinguish between the two. This is a PNP, I'm sorry, NPN, and this is a PNP. Now obviously you can see the big difference is where the arrow is pointing. I like to remember it this way. The arrow that's pointing out, it's not pointing in. That's how I have my students memorize it, not pointing in. NPN, this is your symbol for an NPN. And the other one is pointing in, and that's just a PNP. There's only 2, so that's fairly simple. Your pinouts, your emitter, base, and collector that are associated with this, this is your collector. That's a C, believe it or not. This is your emitter. Those look the same. Sorry about that. And this is your base. Same thing over here. This is your collector, this is your emitter, and this is your base. Your emitter always has the arrow on it. Your base always is the middle pin. Well, I shouldn't say. Again, you have to look at the specification in order to make sure you guarantee the pinouts. Most of the pinouts are like this, but not always. So you always want to check the spec. Now, what do we use these for? We're going to talk about 2 applications. The one application is simply a switch. The other one is an amplifier. Those are the two main things that we use transistors or bipolar junction transistors for. Now, let's jump over to our water example here. I like to use water. If you've watched any of my earlier videos, you can catch on to that. But let's say this is a pipe. So we have a pipe flowing down this way, and then we have another pipe that's coming in at 90 degrees. We have a valve right here that if we pull on this, it opens. And then this is more of a check valve. This rotates. There's a rotate pin right here at the top. So this kind of opens slightly this way when this is pulled. Now, as of right now, we could have, we could have water in here. By the way, this is our collector, this is our base, and this is our emitter, if we want to kind of line it up the way we have here. And this is an example of an NPN. I'm not going to do one for a PNP, but this is an NPN. So we have the water sitting here in the pipe, just waiting. And then all of a sudden we get a little trickle of water through here. Just a little trickle. Now, depending on how much water we have, will depend on whether this little check gate opens. Now, in reality, what we need is 0.7 volts if we're talking realistic. But let's say we don't get enough water. We don't get enough water on that base. In other words, we're less than 0.7 volts. That check valve is not going to open. It takes at least 0.7 to start to open that valve. Now, let's say all of a sudden we get 1 volt. So we get a little bit more water here, and that gate opens just a little bit, and it opens just enough to let some water trickle through. That is enough. If this gate opens and it pulls down on, or let's say this is a pulley, if it pulls down on this pulley, this begins to open. And it's just going to open a little bit because we only have 1 volt in there, so a little bit of water is going to flow down through here, and it's going to add up with whatever came out of the base, and it's going to now flow out the emitter. But as you can see, as more water flows into the base, i.e. more current, that valve, if it opens all the way, this then will open, which will pull this pin, and now we've opened up this valve completely, and everything that's in the collector is now mixing with the base and flowing out the emitter. That is how a transistor works. This is our base, this is our current. As soon as our base sees 0.7 volts, it starts to open up the collector, and the collector then will start to allow current to pass, and that will add to the base and go out the emitter. The more voltage we have on the base, the more current we're going to get through the collector, which means the more current we're going to get out the emitter. So mathematically, we're not going to really spend a lot of time on the math, but mathematically, the current in the emitter is equal to the current in the collector plus the current in the base. And as you can see, what we're really doing here is we're amplifying. If we're measuring current right here, we're taking a small current, a little bit bigger current, and we're amplifying it and making it bigger coming out the emitter. All right, I hope that makes sense. I like that example. I like this little example of the valve here. But now let's get to a couple examples. So you've seen this circuit before. We've used this. You close this switch and our LED comes on. We have our current limiting resistor in there. Everything is good. But let's just say we don't want to use this switch. We don't want it done manually here. Instead, we want to use a transistor to turn this circuit on. So we could then get rid of a couple things here, and I'm going to redraw it. So let's just take this directly over, but instead, let's right here, let's put an NPN. We're going to take that back to, that's a horrible line. And then we're going to tie this just to a battery. And then we're just going to put that to a switch. Now what's going to happen, and again, I am using a switch, but I'm going to give you a different example of that in just a minute. Right now, the battery would love to light that LED, but it can't. And it can't because there's a gap right here. That's an open circuit. Current is not being allowed to flow from the collector to the emitter because the base is not turned on. But as soon as we push this switch, we then get current flowing out of our battery through our base to our emitter back this way. And when that happens, then current can flow from the collector to the emitter, and therefore you get current flowing around the circuit and lighting the LED. So again, you push the button, that turns on the base, you get your 0.7 volts or higher. That turns on this transistor, which means current can then flow from the collector to the emitter, back to the ground here. We're talking about conventional flow, by the way, and we can light our LED. Now, here again, we use an example of, well, this is just a push button. Here's a nice thing. You could replace this with a sensor. Maybe it's an automatic switch. Maybe it's a heat sensor. Something else that closes that then will, light a light. This could be a security system. This is a switch you have on a window. When that switch closes, that light goes off, but here you have a buzzer instead of a light. There's all kinds of different things you can do with the circuit. You could take all of this out, the battery and everything, and have a microprocessor over here. Maybe you're familiar with Arduino or something like that. You could feed that microprocessor into that transistor and turn it on via the microprocessor through a program. All kinds of different options. Now, here's a couple other examples I just want to show, very similar to really this one up here, but this shows the difference between the NPN and the PNP. So here again, we have an NPN not pointing in. There's our base, there's our collector, there's our emitter. As of right now, nothing is lit, okay? But if we push this button, our base turns on. So then we get current going through here, through the base to the emitter, back, which is going to turn that light on. But what also happens, since we applied power to the base, it's going to turn this transistor on, which right now is acting like a switch. And that switch is going to allow current to flow from the collector to the emitter, this way back to the battery, and it will also light this LED. Similarly over here on the PNP, when we push this button down, we're going to get current that travels down through this way and turns on that LED, and we're going to get current traveling down this way and turn on that LED. Now, for example, let's just say we decide to pull that resistor right there. If we pull that resistor and push that button, we're still going to light this LED, because remember, the current in this PNP is going to travel from the emitter to the base. And a PNP, or an NPN, I'm sorry, it goes from the base to the emitter. So very versatile. If you are familiar with microprocessors in general, newer microprocessors literally have billions of transistors in them, and they are what do all the switching, all the amplifying, and all the power stuff that a microprocessor does. All right, that is transistors. Again, this was more of an introductory introductory level, but let's review real quick. Transistors, there's a couple different types: bipolar junction transistor and a field effect. As it pertains to the bipolar junction, you have 3 pins, an emitter, a base, a collector. There are 2 types, an NPN and a PNP. You can see the symbols for each one here. If you're more interested in all that current flow on the P-type and N-type material, you can look that up. I'm not going to cover that here. We went over using our water example of with a couple switches or a couple valves to show how water would flow, and really what we're talking about is the current flow. And then our examples, we have a circuit that we just simply turned on an LED using a transistor, and we talked about we could also put a processor on there. We could use a sensor or something to make the circuit turn on. And then we just show the difference between an NPN and a PNP. All right, that's it for transistors. If you have any questions, please leave them in the comments. And as always, please subscribe to Spreader Web Education.